Okay, this is lesson 6.6, modeling with trig functions. So let's look at a couple examples. A small windmill has a center 6 meters above the ground and blades that are 2 meters in length. In a steady wind, point P at the tip of one blade makes a complete rotation in 12 seconds. If the rotation begins at the highest possible point, determine a function that gives the height of point P above the ground at a specific time t. So in order to do this, we need to be able to do two things. First one is we need to be able to sketch a diagram and use that diagram to produce a graph. And secondly, we need to be able to generate a formula from that diagram. So we know that our formula is going to take on a specific form. And one of the keys is to figure out whether or not we're working with a sine or a cos function. And since it's asking us to begin our graph at the highest possible point, when you start at a max or a min value, it's easiest to use cos as your base model. So that highest possible point should hint to you that it's going to be a cos as the base function. And that's because the cosine function actually starts at a maximum. If it started at a minimum, we could just reflect the cos function and then use the cosine function with a vertical reflection. If it doesn't start at a max or a min, it starts somewhere like at the axis value or close to the axis value, we'd use sine because that's where sine starts. So in this case, cos. First step, let's try to draw a diagram of what we're actually talking about here. So we're actually going to draw a windmill. I'm going to draw a really simple windmill because I'm not an artist, but we know that the center of the windmill is 6 meters above the ground. So I'm just going to draw a dot. That represents my middle. And I'm going to draw that dot 6 meters above the ground. And we know also that the blades on this windmill are 2 meters in length. So that means if I draw one blade straight up 2 meters, that's as high as we could go. And if I draw one straight down 2 meters, that would be as low as we could go. And I'll draw a couple other blades on there for good measure. There we go. That one looks a little long. Let's shorten that one up a little bit. There we go. There's our windmill. And we can use that diagram to help us start to construct the graph. How can we use that? Well, if we know the center of the windmill, that should be the center of our graph. The center of the windmill being 6 meters above the ground tells you something about the function. That actually tells you the axis. The axis, or the C value, must be 6. And if the blades are 2 meters in length, that means above 6 we could go 2 meters up or 2 meters down. That's telling you an amplitude. An amplitude is 2 meters. It's also telling you the radius of the windmill, and radius and amplitude are always related, especially in trig. If you know the radius, you know the amplitude. If you know the amplitude, you know the radius. So there we go. Now we know A and C, so we know the amplitude and the axis value just from what we're given in the question. The last thing we can pull out of that question is we know the period, or at least we can find the period. We know this relationship. We know that the period is 2 pi over k, and it tells us that we do one complete rotation in 12 seconds. A complete rotation means one rotation, and one rotation is the definition of the period. So we know 2 pi over k is 12 seconds. And we already said that the amplitude was 2, which would make our max 8 meters, and our min 4 meters. Since we're starting at a maximum, the only place to rotate is down, so this graph is a cosine graph started at a maximum. Our y-scale, we're going to use h to represent height and t to represent time. So this function is h at t. And we have some heights, and our time is in seconds. Height is in meters. So here we go. Now we can start to graph. Since we know this is going to look like a cosine graph, since we're starting at the highest possible point, we're going to start there at 8. And we know after one complete cycle, 12 seconds, we're going to end up all the way back at 8. So now we ask ourselves, when will the function be at a minimum? Well, the cosine function starts at a max, goes down, and then back up to a max, and that's one complete cycle. And the nice thing is it's kind of symmetrical within its own period. And we know then that our minimum is going to be halfway between the maxes. So 0 and 12, right in the middle is 6. So at 6, we're going to reach a minimum. And we have our axis at 6. I'm going to draw that on. And then we can see our amplitude on the graph. That's c equals h of t. H of t equals 6. That's our axis. And just as we found where the minimum is going to be, we'll find where we're back to rest. We're back to rest between it going from a max to a min, which would be right in the middle at 3. So that's where we reach our axis. And over here again, we'd reach our axis between 6 and 12, which is 9. So there's some dots to make our function, and we know it's cos, so we're going to follow a nice smooth curve like cosine. So we're going to go down, reach a minimum, go back up, and reach a maximum. And there's what one cycle on our windmill would look like. To generate the formula, we want to model it like this, with an A, not sine, a cos k, and then we're going to put in times, not angles, so t minus d plus c. And we want to find a, k, c, and d and input it so we have a nice formula here. So let's see if we can do that. What is A? A is your amplitude, which was the radius or the length of the blade, so that's 2. Cos k is your horizontal compression or stretch, and we can solve for k. We just have to do a little bit of math. 2 pi over k equals 12. So we need to swap spots here by cross multiplying, and that would give us 2 pi over 12 equals k. And if we reduce that fraction, we get pi over 6 equals k. Oh, look what I just did. I wrote right in the way. So I'm going to take this out of here. Finish this off to the side here. K equals pi over 6. There's our answer. And now we can put k into our function, pi over 6. Do we have a d? Our horizontal shift in this case, since we're starting at a max and cos starts at a max, we haven't shifted away from that, so we don't have a d. So this is just pi over 6 times t. C is your axis. Our axis was 6 plus 6. And there's our function. All right, let's see if we can answer a couple questions about our windmill. What is the height of the point at 5 seconds and at 40 seconds? Well, all we need to do to find this is we can look at our graph and estimate. It should be just above 4, definitely less than 5 though, but that's not an accurate enough representation, so we should probably use our equation. We have an equation that tells us heights at certain times. We want the height at 5, so that would be 2 times cos pi over 6 times 5 plus 6. And if we type that directly into our calculator, making sure that our calculator is in radian mode, we get approximately 4.268, and that's in meters. And we can do the same thing for 40 seconds. Height at 40 seconds, 2 times cos pi over 6 times 40 plus 6. If we plug that one into our calculator, we get exactly 5 meters. So that's using an equation to solve for h Alternatively, we could do the exact same thing. If given the height, what would the time be? So here we go. We're just going to look for an answer in the first cycle. So let's see what we can come up with. At what time is P exactly 7 meters above the ground? So that is a height of 7. So that's when does 7 equal 2 cos pi over 6 t plus 6. Now we just have to do a little bit of rearranging. Subtract 6 from both sides. We end up with 1. Divide both sides by 2. We end up with a half. And now we have to do cosine inverse. Cos inverse of 1/2. There is a special triangle that has 1 and 2 on it. And if you do cos of pi over 3, you get 1/2. So that our answer is pi over 3. And on this side, cosine inverse of cos is just whatever the input is, which is pi over 6 times t. So something times pi over 6 gives us pi over 3, and we can find that by dividing. Pi over 3 divided by pi over 6. And that would give you 2. So at time 2, we are 7 meters above the ground. So let's go compare this up here with our graph. At time 2, boom, 7. Yeah, it looks pretty close on our sketch here. But if we continue tracing, we do hit 7 again, up in here around 10. And the question is, how do you get that second answer? Well, you actually use the Cartesian plane to figure it out. We know that we were looking for cosine inverse of a positive ratio. So we know we're looking for where cos is positive. According to the cast rule, cos is positive in quadrants 4 and quadrant 1. And if we look on our graph, quadrant 1 would be the first section of our graph, and quadrant 4 would be the last section of our graph. And that is actually where cos is above the axis. So that shows you where it's positive. So question is, how can we find that on the Cartesian plane? Well, if we do one whole cycle in 12 seconds, let's graph one whole rotation as 12 seconds, which would make half a rotation as 6 seconds, a quarter as 3, and 3/4 as 9. Our first answer was at 2 seconds. At 2 seconds, P had a height of 7. And that was a 2-second turn. If you think of seconds as an angle, we're rotated 2 seconds on a 3-second scale. That's kind of like your beta or your related acute angle. If you graph that same angle in the fourth quadrant, the remaining angle here would be 2 seconds. And we know it's the fourth quadrant because that's the other one where cosine's positive. So that means if we were looking for our theta, or our angle that we're rotating all the way around, we'd be 2 seconds short of doing a full rotation. A full rotation is 12 seconds. 2 seconds less that is 10. So our time 2 would just be 12 minus 2, which is 10. So there's actually 2 answers to this question. If it asked the first time that P was 7 meters, the one answer is appropriate. But since it says what time is P 7 meters above the ground, and we've drawn one complete cycle, we should give the full solution, which is both times that we are actually at 7. So there are 2 solutions. If it is general like this, it may even want you to write a series for where all the possible 7s are. But in this case, the question was supposed to mean within the one rotation, where is it at 7 meters? And that's how we find our second answer, and our first answer just comes from rearranging and solving the equation. All right, that's example 1 from our lesson. There will be a second video for example 2, if you want to tune in for that one. And the third example I'm going to ask you to do on your own, and then check the solutions on the course website. Thanks for watching, and I'll see you in part 2.